Hello, everybody. Thank you so much for joining us. We are so excited to get started. As you settle into the Zoom room, feel free to use this time to grab a drink of water. I know we're still waiting on some folks to join us. As everyone's settling in, I do want to direct you to the bottom of your Zoom window. At the bottom of your Zoom window, you'll see what looks like a little chat bubble. And if you click that, that will open our webinar chat. In the webinar chat, that's where we're going to be answering our questions today. Now, if you've clicked on that little chat icon and it's populated the chat box, you may see on the bottom a little blue button. That right now might be set to two hosts and panelists. That's to whom your chat is going. I'd love to encourage you to go ahead and click that blue button and make sure that it's set to everyone. We want to make sure your questions are going to everyone for two important reasons. One, we really want to make sure that we are building community. If you are asking a question, if you're wondering something, there's probably a teacher in the room that is wondering the same thing. They might not be sure it's okay to ask a question, so you are helping them see like, heck yeah, this is a community. We can definitely share ideas, give our ideas, have our questions. The second reason we ask you to set that button to everyone is so that as we answer your questions, we don't look like we're talking to ourselves. So please make sure you're sending your questions to everyone. With that being said, let's go ahead and practice that skill. Go ahead and navigate to the webinar chat in this room, and let me know what your favorite dish at Thanksgiving was this year. Mine was pumpkin pie with just all of the whipped cream. That's really where it's at for me. Let's see. Trisha shares candy yams. Yum. Let's see. Nadine says stuffing. Yeah, that's the good stuff. Trina, good to see you, Trina. Chicken casserole. Yum. Oh, no turkey. That's great. Bryce says stuffing. Let's see. Kevin shares mashed potatoes and gravy. A classic, Kevin. Jessica shares cranberry apple bake. Ooh, that sounds like a recipe I'd like to look into. We've got folks letting us know that they loved spinach this year, pumpkin pie, great call, John. Mashed potatoes, pumpkin pie, thank you, Jim. PA, Dutch bread stuffing. I will need to look into this unique twist. Definitely the stuffing, says Stuart. Green bean casserole. I had two green bean casseroles on my dinner table this year. Loaded stuffing, says Jean. Homemade cranberry sauce. John says, yes, all of it. And you know what? Heard, John. I totally agree. And Glenda shares apple pie. Very cool. Well, I hope you all had an amazing holiday week. I know that we've been excited to get back and get into this webinar with you all. So that being said, we're about 2 minutes past the hour. So let's go ahead and kick it off. If Josh, are you sharing the slide
Yeah.
deck?
All right.
Perfect. I think we have some housekeeping items to touch on, and then I will pass off the presentation to today's experts. So you will receive a recording of today's webinar. It usually takes us about 3 to 5 business days to get that edited and uploaded. And as soon as it's live, it's going to be live both on our YouTube channel and our website, so you can find it there. When it's ready, I'm also going to email it to you. So keep an eye on your inboxes. In about 3 to 5 business days, you'll get that recording to your inbox. In that email, I'm also going to include a link to today's resources folder. The resources folder has today's presentation with clickable links. It has a certificate of attendance and lots of experiment files. So I'm actually going to drop that link in the chat as soon as I'm done talking. So keep an eye out for that. And I'm happy to reshare that at any point today. And as I mentioned before, we would love to answer your questions during today's presentation. Please use that webinar chat to go ahead and drop your questions in there. If we happen to not get to your question, or if you have a follow-up question, you think of something later after the session is ended, go ahead and email us at physics@vernier.com. The last piece of housekeeping I want to include is that we are going to be giving out $100 in Vernier technology at the end. It'll just be a gift certificate. So make sure you stay till the end. I'll be randomly selecting someone who is still in the webinar at the end. That being said, I think we're good to go. So please enjoy the presentation and thank you so much for enjoying us.
Thanks, Dylan. We Let me go here. We're going to do a quick survey. I kind of want to know a little bit about you and what your uh, how much you know about Vernier technology and how you're using it and that sort of thing. While you answer those questions, I'll just do a quick introduction for myself and for Fran. We're both former high school physics teachers. We both taught on the East Coast. Um, we both love physics, you know. Dylan mentioned that email address, physics@vernier.com. If you email us at that email address, you're going to get Fran or me or a couple of our colleagues here at Vernier. We're pretty much all uh, uh, physics folk. We understand, we've been in the classroom, we understand kind of how you might want to use the equipment, how you are using the equipment, and we want to be able to help you. Sometimes that's through just answering, emails and chats or phone calls and that sort of thing. We act as teacher advocates in the kind of like the product development process and here at Vernier. And then we also do teacher trainings like this and at conferences. And if you are, if you this kind of wets your whistle and you want to have do a deeper dive with us one-on-one, we do lots of Zoom trainings, like a 1 hour complimentary Zoom training. So if that's interesting to you, you can, there's a form on our website, I'll point it out later, where you can request a training like that. Okay, it looks like we got a lot of Vernier users here. It looks like nearly everybody says they use at least Vernier equipment regularly or occasionally, Uh, I was curious. It looks like we got a lot of high school teacher, a lot of a significant number of college AP teachers. That's great. The subject we're doing today, rotation, is usually done as a high school or an AP subject. Where there are a lot of ideas that are really accessible to everyone. So it's kind of a fun thing to do. I asked this question about when you do lab work, mostly out of curiosity. I was thinking about it the other day. When I was in the classroom, I often started off a new unit of study with like a lab, some sort of hands-on thing, just to kind of get things going. It was fun, especially since usually a new unit of study followed like a test or something like that, and it was nice to like get up out of your seats and be doing something rather than being sitting down on a pencil and paper again. And then I would find that I often use them sometimes in the middle of a unit of study to kind of like explore ideas. We've talked about some things, we've had some experience, and now we want to do something quantitative and like start drawing, getting numbers down, that sort of thing. One place where I didn't often use lab work though was at the end, like a practicum. And that's something that I feel like I kind of missed out on. And so I was kind of curious to see how many of you use lab work kind of at the end like that. I will say, I taught a conceptual physics class for many years, and I did in our electric circuits, unit. We would always one of the unit end of unit evaluations we would do is we would put together a circuit and we would break it certain ways and we would pull students back one at a time and they had to troubleshoot and fix the circuit, and that was a great hands-on way. I found that a lot of students that they like that, especially compared to like the pencil and paper test. Anyways, I just want to get things percolating. If you have a particular end of unit practicum that you love, feel free to post it in the chat. I'd love to hear how you use those sorts of things. In the meantime, I want to talk a little bit about the rotary motion sensor and a couple of activities. This webinar is focused primarily on rotational motion, conservation of angular momentum, that sort of thing. We're going to use the Go Direct rotary motion sensor as the primary focus tool that we'll be talking about here. And I want to demo a couple of lab activities that we have from one of our um, physics lab books. And we'll have time at the end for question and answers. What I'm going to do today is primarily spend my time demoing these activities, but I'm hoping that as you have questions, we'll be able to do a little bit deeper dive into what's happening. as Dylan mentioned before, if you've got questions, please put them in the chat. All right. So the rotary motion sensor, that's kind of like what we're going to use the tool today. It's this kind of box, and it comes with this three-step pulley. And that pulley is kind of usually what you use to attach it to various apparatus. We make an accessory kit that includes this rod and these kind of cylindrical masses that go on there. Um, and these discs, it comes with a pulley that's popular, and this kind of like swivel mount here you can use together to do like a torque, a Newton's second law, torque activity sort of thing. Today I'm going to use, in the conservation of angular momentum lab activity, I'm going to use these discs. And then in the activity that uses the kind of the grandfather clock physical pendulum activity, I'm going to use this rod and these cylindrical masses here. Uh, the rotary motion sensor actually has two modes to it. There's kind of like a high precision mode. That's this one where you get a resolution down to a quarter of a degree. Um, for most activities that the standard mode is enough, I'm going to use that high precision mode for the physical pendulum activity just because it gives us a little bit cleaner data. There is what we would call a LabQuest version of the rotary motion sensor. It looks very similar to this, except it's entirely black, and it connects to a LabQuest interface, like a LabQuest 3 or a LabQuest Mini or that sort of thing. And the activities we're doing today will work just the same with that LabQuest rotary motion sensor as it does with this GoDirect version. The GoDirect sensors are kind of like our latest and greatest, and they're convenient in the sense that they connect via Bluetooth or USB, so there's just less cables hanging around. And that means they also can connect to just about any device that you might have in your classroom. One last thing I guess I'll mention about the rotary motion sensor, there is a little motor accessory kit that you can attach to the side of the rotary motion sensor to drive it at a constant speed. And that can allow for some investigations that you might not be able to do otherwise. I'm going to first, I'm going to switch gears here a little bit, and I want to show you my we're going to switch here to this apparatus for the conservation of angular momentum. So I have set up here my rotary motion sensor, and this all black version is our LabQuest version. You can see that it uses a BTD connector, one of these guys that plugs into a LabQuest interface. Otherwise, it works just the same. And so if you got those, you can do the same activity. This particular activity is the idea is conservation of angular momentum. So the way that this works is students mount one of these aluminum discs onto the rotary motion sensor, and they spin it. I put a couple of pieces of black tape on here just so you can see it spinning a little bit easier. Spin it, and then they drop the second washer on top and change the moment of inertia very quickly and look to see how the angular velocity changes. So the idea is that you start off with a certain amount of angular momentum determined by how hard you press this thing, get it going, and then the angular momentum is conserved, but obviously the moment of inertia changes there, and so your angular speed changes as well. Students measure, the rotary motion sensor will measure the actual angular speed. Students change the moment of inertia by dropping the second disc on top. And they do it a couple of times. First, they do it like, at one speed, and then they do it again at either a faster speed or a slower speed to see if how that speed changes it. And then you can also, instead of using an aluminum disc like this, you can also mount on the rotary motion sensor. This is a big steel washer. It's noticeably heavier than these aluminum discs. And so you can mount that on there as well. That way, rather than the mass doubling, it only increases by about 50%. So that's the second part of the activity is to use this steel washer instead. I want to collect some data so you can see what this is like. I'm going to connect to graphical analysis. I'm first going to turn on my rotary motion sensor. I'm just going to press the little power button there, and a little red LED comes on. That means that it's on, but it's not connected to any device yet. And now I'm going to switch to graphical analysis. Graphical analysis is kind of like our core data collection and analysis app. And I'm just going to use the version of graphical analysis, the web version, that just runs within the Chrome browser. So that's this here. You can see that I'm still in Chrome, and in the address bar, I typed in graphicalanalysis.app.app, and it just loads the app from within the Chrome browser. That's really nice because I don't have to worry about installing it. I'm here in our studio. I don't necessarily have like admin privileges to this computer I'm on right now, but that's okay because I can just pull it up within Chrome. I want to connect to my rotary motion sensor, so I'm going to choose sensor data collection. And I want to connect wirelessly, and I need to choose the, the probe that matches the one in front of me. Mine has an ID that ends with 0G8, and I can see this very first one listed here. That's the one I want, 0G8. I'm going to pair with that, and I'll connect to this probe then via Bluetooth. Um, I'm going to hit done here. And I can see I've got two graphs, velocity and angle, both radians. Radians is kind of like all of our probes default to SI units. So that's kind of where we're at. I can see that the default data collection settings are such that it's going to record data for 10 seconds. That's probably pretty good. I'm not too concerned about the angle, but I am primarily concerned with my angular velocity here. So I'm going to change this a little bit, and I want just one nice big graph here that just shows angular velocity. And I'm going to do that by, in the upper right hand corner here, I'm going to choose this box of boxes where this is called the view options menu. And instead of the graph, I'm going to change just to one graph. And I can see now I just have velocity versus time. If I want to see a data table, this is where I would turn that on. If I want to show the angle really large, I can turn on a meter. If you want to insert a video, that's what this is. I'll show you why you might want to do that later. And then if you want to make notes to yourself, like this is what I was doing, or this was the mass of the aluminum disc, and this is the mass of the steel washer, and so on and so forth. You can do that in a notes field like this. I'm just going to leave for now. I'm fine to leave it just out like this. Um, I'm going to I'm going to take just do I'm going to first just hit collect here and collect some data and see what it's like, and then I'll go and try it by dropping that second disk on. So I'm going to just hit collect here, and I'm going to spin this thing up. It looks like I spun it in a what would that be? A counterclockwise direction. So now I have a negative velocity. From my graph, I can see when I hit start, it wasn't moving at first, and then I spun it, and it dropped really. The velocity dropped. I can see if I pan along here, I can see that my velocity is slowly going back to zero. That makes sense, right? There's a little bit of friction in the bearing there, and so it starts just slowly slowing down. If I wanted to know, for instance, what the slope of that was, like what was the angular acceleration or the rate at which it's slowing down, I could click and drag this region here and do a curve fit. And that curve fit, a nice linear curve fit, that's going to tell me the slope of that in radians per second per second. At what rate is it slowing down?
Josh, there was a question.
Yeah.
When you switched the display to one graph, how did it know to pick V versus T rather than
Ah,
angle versus T?
that's a
And
good question.
yeah, I don't actually know the answer. So my response was, Jonathan, good question.
I don't know that. I'm sure that there's some sort of rhyme or reason to that. I think for each sensor, there's probably like a primary graph that's chosen, and for this particular sensor, like velocity versus time is usually what you're using this for. And so probably that's why it defaults to velocity versus time. Like if you use a motion detector, it defaults to position versus time. Um, I find that if it picks the wrong thing, and that happens, like I want, maybe I'm doing some kinematics activity and I want to see just velocity versus time and it's giving me position. If you click on the vertical axis, here where it says velocity, you can choose what data to display. So angle, velocity, or acceleration. Um, it got lucky this time, and it chose velocity. But if I wanted to, I could choose, angle and turn that off and just have my, the angle versus time. I'm going to stick with velocity this time. And I'm going to do this again this time, but this time what I'm going to do is I'm going to set it spinning. Like it doesn't, I mentioned before there's like a motor kit. This does not have the motor kit attached to it. I'm just getting it moving just on my own,
Yeah,
with my hand here.
and Josh, Nadine actually asked, how did you start the motion? So is there anything
Oh,
specific that you're doing there?
nope. All I'm doing is just using my finger to get it started. And so I'm going to, the second run here, I'm going to get it going. And then I'm going to take and I'm going to drop my second disc on top. And you'll see there's a hole in the middle here. That's so that it drops down onto, on the post there. So it's nice and centered and stuff like that. I'm going to try to do this as smoothly as I can. I know I'm never like perfectly going to drop it on there. And so there's always going to be a little bit of a blip. But the great thing about the laws of physics is they always work. And so momentum will still be conserved no matter how poorly I drop this thing on here. Unless I really break things. So that's what I'm going to do. I am going to change one thing here in graphical analysis. I like spinning it this way because I'm right-handed and this is on on this side of my body, and so I want to do it like this. But I want it to be positive. I want, instead of reading a negative velocity, I want to record a positive velocity. So what I'm going to do is, I don't need this little curve fit. In the lower right corner, it gives me an angle measurement here. This is like a live readout of what it is. And I've been spinning this thing for so far now, I've gone through, it looks like 2,800 radians. I'm going to choose that. That's actually a menu there. And I can like zero this out if I want. I can also reverse it. So now when I spin this guy with my preferred direction here, it gives me positive values. You'll notice there's another option here where I can have it reset to 0 when I hit collect. There's some experiments where that's handy. I'm actually going to, I don't know if we actually need that one today, and then there's also, if you want, you can switch from units, from radians to degrees to revolutions. So I've got reversed right now. I'm going to zero that out one last time. Okay, so now I'm ready to go. I'm going to hit collect. I'm going to hit this thing running, and then I'm going to drop this second washer on top as best I can. So that's my plan. We'll see how we're doing here. So I'm going to hit collect. I got this guy spinning, and now I'm going to drop this on as best I can. And there we go. Okay. So there we go. That's a pretty good looking graph there. I think I did a reasonable job dropping that disc on there. It's good because I'm doing it in front of all these people. So this graph is interesting. It looks like kind of stepwise. If I were to look at the angular, the position, the angular position, I'm going to turn off velocity and turn on angle. You can see it's got some kinks in it, right? There was one speed or I guess at first it was at rest, and then I started it going. And I'm at one speed here, and then this kink here is when I dropped the disc on, and now it's at a smaller slope, a lower speed. I'm going to go back to the velocity data because that shows the same thing a little more clearly, I feel like. You can see, if you look carefully, you can see that this speed here, just like before, it's slowly slowing down. There's just a little bit of friction there on that bearing, and so in the rotary motion sensor, so it's slowly slowing down. It's losing angular momentum to the area around it. And then I dropped it on, and it dropped down to the bottom. My two discs here are just about the same mass. They're not identical. The two discs aren't identical, but they're pretty darn close. And so I would expect as a physics teacher, maybe not as a student, but as a physics teacher, I would suspect that if I double the mass, I would have the angular speed because, angular momentum is I times omega, moment of inertia times the angular velocity, those two quantities. So if I double my moment of inertia, I should have my angular speed in order to keep that quantity conserved, the same, overall the same. And if I look just before I dropped, I'm at about 37. And just after that I dropped, it's about 19. So that's pretty good. That's pretty good. That's just about half of what I would expect. I should say, that's what I would expect. I've got just about half the speed. Um, if you do this with your students, you might ask them about this slow, what's happening here? Why is this decreasing? You would have them do this again, probably at, you'd have them do it at slower speed or at a much faster speed just to confirm their first results. And then you would use the steel washer instead of the aluminum one, just because this one's so much heavier. That would be a drop. When you drop this on top of it, the mass only increases by about 50% rather than by 100%. So you would, is momentum conserved in that situation as well? That's kind of how you would use it. That's kind of what we get to. Let me point you to the Google Drive folder where we have this lab posted. I'm going to go to the folder itself, and it looks like we might need to. I can post this real quick here. I think I can. I
I
know how
got
to.
it.
You got it?
Yep.
Okay. In the Google Drive folder, you will see that there are a couple of PDFs. They all start with this prefix PHYS-AM. That's kind of our order code for the Advanced Physics Mechanics lab book, kind of the lab book where these labs come from. And you'll see that there are two documents for each lab. One of them ends with an I, and that one is the instructor notes. And the instructor notes includes, the sample data and setup tips and that sort of thing, as well as answers to the follow-up questions. The one without the I is the student handout. This is what you would actually like print off and hand to your students to do. So we're doing this conservation of angular momentum activity. That's this one here. I'll make this just a little bit bigger. And
Josh, I
yeah,
got another question.
sure.
Jonathan asks, the velocity curve showed the drop when the disk was added, and it looks like the change took about 0.25 seconds total. Do you know if that represents slippage or is it maybe due to the sampling rate?
There's definitely going to be some slippage right at first. The sampling rate is important, but perhaps the reason why you see it happening like that is because of the way graphical analysis calculates the angular velocity. What the rotary motion sensor is measuring is just position. There's like an encoder in there. It's watching these stripes go by, and from the motion of those stripes, it's figuring out how far the disc, the axle has turned. And then it sends that data to graphical analysis, and graphical analysis then takes that position data and uses that to figure out the angular velocity. And the way that it does that is using a numerical derivative. So let's look at, we'll do something a little more. So if we look at 2 seconds into our data collection here, at that point, the rotary motion sensor said, okay, it's turned a total of, this is data set 1. I want to go over to data set 2. Here we go. At 2 seconds in here, it said it's turned a total of 44.47 radians. That's how far it's spun at this point. And what graphical analysis did was it looked at that data point, this 44.47. It reached back 3 data points in the past, and then it reaches 3 data points into the future, and it does a curve fit over those 7 data points. Did I grab 7? Or ish. Did I? I might have grabbed the wrong rows there. It takes these 7 data points, and it does a quick curve fit, a linear curve fit on those 7 data points, and it takes the slope of that little curve fit and plugs it in for the velocity at that time period. So it's kind of centered on that particular one. Because it's reaching into the past and reaching into the future in order to find the velocity at that point, you get a little bit of smoothing through it, you know? So really abrupt changes get smoothed out a little bit, you know? And usually that's fine. You know, usually things happen slowly enough that that smoothing isn't a big deal. There are times when you have really abrupt changes and you get that smoothing is too much. For those of you that are designing experiments where you anticipate really abrupt changes like that, you can sample faster, which usually works. So depending on the device, there might not be able to, there might be a maximum to how fast you can sample. The other thing you can do is you can actually change how graphical analysis calculates a derivative. And that's from the settings. If you go to, I think it's session settings. Yeah. You can change the number of points used for derivative calculations. The default is 7. You can down to 3, you know, where it just uses the data point before and after. But you could really smooth things out, you know, to get real curvy, smooth sort of derivatives by using 21 data points. I don't know. I don't know if you would ever want to do that, but so yeah, there's probably some slippage here. We could maybe sample a little bit faster in order to get more data points in there. And then it's also just because the way that the derivatives, it gets kind of it gets smoothed out a little bit there. All right. So the activity has students doing those different things. Now, I want to talk a little bit more about this particular activity because this is kind of parallels something that we often talk about when you talk about the conservation of angular momentum. Kind of like the classic, right? The classic, what classic real world example of conservation of angular momentum is the figure skater. You know, you might show a video of an Olympic skater out there on the ice and they jump into the air and they're spinning and they pull their arms in or they let them out and their speed very obviously changes as they they change the shape of their body. And we talk about how as they move their arms in and out, they're changing their moment of inertia. And because of that, because of the law of the conservation of angular momentum, their angular velocity has to change as well. That's really cool. And this particular activity is very similar, right? We're changing the moment of inertia by changing the mass, by dropping this second disk on top. But it would be kind of cool to be closer to how a figure skater actually does that. And we don't like offer this as a product, but Dave Vernier, if you've ever met Dave, you know he likes to tinker. And so he built himself a mechanical figure skater. We call it the Arduino Ice Skater. I've got it mounted right now on top of a rotary motion sensor here. Sandwiched down in here, kind of on the base of this board, is a Arduino microcontroller. And it's running it runs a very simple program. All it does is tell the servo motor here, to turn one way and then turn the other way. And the rest of the Lego Technic pieces here are so that as it turns one way, it brings its arms in and then brings it out. There are just some, these are actually little rollers that are intended for wheels with a Lego Technic robot. But here we're just using them as masses. Let me show you what that looks like. I'm going to turn this on here. You can see it just raises its arms. Let me move this up a little bit more. And then it closes it and then raises it back up. And so if you get this guy spinning, you get that same sort of figure skater, sort of like the angular speed changes as the arms raise and lower, which is pretty cool. This is all it does, is it just opens and closes its arm. So here we go, the Arduino Ice Skater. Now that's cool, but I collected some data with this. Obviously, I've got a rotary motion sensor here. And so I collected some data with this earlier, and I'm going to show that to you now. I'm going to take this guy. I'm going to come back to graphical analysis, and I'm going to, this is all great data and all, but I'm going to close out of it. I'm going to disconnect from my rotary motion sensor, and I'm going to go to, so I mentioned before, I showed this view options setting here in the upper right corner, the sensor options in the lower right. Lower left is where you change your data collection settings, like how long you're collecting data or how fast you're collecting data. And then the last real menu here is the upper left-hand corner is the file menu. And this is where you can save your data, export it as a CSV file to open up in Excel or something like that. I'm just going to choose New Experiment. And I'm going to, as beautiful as this data is, I'm going to hit Don't Save. And I'm going to now open a saved data file. I'm going to choose a file here. And the file that I want to open is called Arduino Ice Skater. I downloaded it to this computer a moment ago. If you go to the Google Drive folder, you'll see that one of the things in there is this Arduino Ice Skater.gambl file. You'll also notice, if you're paying attention, that that file is 50 megabytes. It's significant. And the reason for that is there's a video embedded in it. And the video is like, takes up most of that storage. I've opened it up here. I've got this video that I took earlier. I've got some data that I collected from it earlier. And I can put those two things together. I can show the video and the data collection at the same time. This is a feature from that's available in Graphical Analysis Pro. Graphical Analysis, most people use it as just the free, what we call the basic version. If you go to graphicalanalysis.app and you just load it up there, you're just getting the free version. If you want to do the pro features, you have to have a license key. If you want to try this out, I put the license key in our slideshow here. This particular license key, it starts TGA. It's good until December 15th. You plug that into the app, either on the very first home splash screen if it's available. Otherwise, you go to the About menu, and there's a place where you can add the license key there. Once you've got Pro, you can open this up and you can have these two things sync together. So here's my video, here's my data. I want to replay the data, and that is also in the upper right corner. There was the box of boxes, that's my view options. Just to the left of that is this circular guy. This is my replay. And if I choose replay, then I have this option to replay the two together. And you can choose at what speed it's going to replay the video at. This is for most physics experiments, the videos are relatively short. If you were a biologist and you wanted to record the oxygen consumption over an hour or something like that, and then you could replay it at, or really at 10x or something like that. But for us, 1x is good. I'm going to hit play here, and my video starts to run, and then once I'll hit collect here, and then I'll start spinning it. And now you get the data and the video at the same time. It's kind of cool. You can see how it slows and then climbs back up. If you click on the graph, the video is synced to it. So as I pan across here, I can see what position the skater is in when it's moving the slowest, and then also when it's moving the fastest. That's kind of cool. If you this is kind of a neat way to do things. We added this feature to Graphical Analysis Pro when during the pandemic, because there are a lot of students were at home, teachers were at school, sort of thing, and an instructor could make a video of the data they were collecting in the classroom and then send that to their students. And the students, even if they couldn't get their hands on the data or on the apparatus, they still got the data, and they had the video of the experiment happening, and they could put those two pieces together, and they could still do like the analysis and follow-up portions of a lab activity. I really like this feature. Makes it really cool. There are some labs that happen really quick, and it's kind of hard to know what happened first and when, like a collision or whatever, how did exactly that happen. And if you have video of it, you can slow it down, and with the sync data, you can kind of put those pieces together.
Josh,
yes.
do you have a moment to talk about linking the graph and the video?
Oh, sure. Yeah. So it's all looks. I set this all nice and pretty up. When I first collected the data, I didn't have the video in it. It's not like I recorded the data from within graphical analysis. I had my phone, my own personal smartphone set up to record it, and then after the fact, I I got my video onto my computer and I inserted it in graphical analysis. I inserted that video, and I went to this spot here. I went to this replay option, and in order to sync the video with the graph, you have to tell it some sort of one moment in time where this point in the graph matches up with this point in the video. And the way that you do that is in the upper left corner, there is a sync video to data button. And if you click on that, it brings up this option where you have a data set time and a video time. And you plug those two things together. What I did was I went here in the video and I looked to where did I start this thing moving? It's like, okay. And I looked at my data and I said it was about 0.085 seconds into data collection is when I actually started doing it. So I said a data set time was 0.85. And then I went in the video here and I looked to see at what point in the video did I start the thing moving. And I said, okay, that was about 8.16 seconds in. And so I plugged those values into this this part of the thing, and it uses those timestamps together to kind of sync the whole thing together. It takes a little bit of there are ways, obviously, like this was an easy way to kind of sync the two, and so usually, often when I create videos like this, I'll start data collection, or I'll be starting my data collection and I'll do something in the video that'll help me know when to sync the data. In this case, when I was actually starting the video, that was the easiest way to do that.
Thanks.
Yeah. Once you've got that set, you don't want students to mess with it. If you click this little button again, it goes away, and then you don't have to worry about kids meddling with that and changing it. All right, so that is the Arduino Ice Skater. Oh, I misspelled Arduino there. And if you're curious about this thing, it's pretty cool. I'm sure Dave would love to hear you and to hear from you and tell you about it. I'm sure he'd be happy to take some pictures and stuff. It's fairly simple, but you have to be kind of a DIYer in order to make this sort of thing. Let me go to this last activity. This last one is all about the grandfather clock activity, the physical pendulum. This particular activity, you use the rotary motion sensor on its side. So I'm going to move this out of the way, and I'm going to bring down this guy. I'm going to move this guy back here a little bit. You're going to turn it on its side and use it as a pendulum. I'm going to make this guy, here we go, on its side. So now it's recording angle, but that angle is the angle is measuring the position of my pendulum bob here. This particular activity has students first, you're measuring angular position here. Use that to figure out the period of oscillation or the frequency of oscillation from that graph. Then it has students kind of look at how does that angular frequency change as I move my bob up my rod here. So they start off with it at the very bottom and then end with it real close to the top. How does that change my angular velocity? And then they look at what if I add a second cylindrical mass to the end here? How does that change my angular velocity? I'm going to do some quick data here just so you get to see what that looks like. I'm again connecting to that. This particular sensor ends with 1F4. So I'm going to go back to graphical analysis. And I'm going to go new experiment. And now I'm going to do sensor data collection again. Wireless. Here we go. All right. For this particular activity, I'm going to use the high resolution just because I'm not going to be, things aren't going to be happening fast here, and that extra precision will be nice. So that's under sensor channels here. This is where I switch from angle to what they call angle high resolution. And for this particular activity, angular, like this velocity, this particular speed is not that important to me. So I'm going to go back to just one graph like before. This time it did choose the wrong, like I don't really want velocity. I'm going to go here and I'm going to change this to angle. And I want this rest position here. I want to call that 0. So I'm going to go down here and I'm going to 0 this out. It's pretty close to 0. And then I'm just going to set this guy going and I'm going to hit collect. And I get this nice little oscillation that looks pretty darn smooth and looks like a sine or a cosine function. I'll make that a little bit bigger here. I got this nice oscillation here. Now what I'm going to do is I'm going to do the same thing, but I want to move the mass. Right now it's kind of at the bottom, and I'm going to move it back up. So I'm going to stop this guy, and I'm going to move this back maybe 2/3 the way to the top. And just by like my own sight, it looks like it's moving quite a bit faster. So I'm going to hit collect here, and it does look like it's coming to happen a little faster there. We'll see. When we're done, we'll show both of these, and then we'll do a curve fit to find the angular frequency here. So I'm going to choose, although this is interesting too, I guess if we wanted to, we could look at these peaks, and we could see how quickly it's slowing to a stop. At the first, it was 0.32 radians. Now it's 0.28. Anyway, so I'm going to go here and show both data sets. Data set 1 was with that at the bottom, and data set 2 with what was it, like 2/3 of the way up there. And I can see just by looking at the peaks, they're definitely, the second data set much more. I'm going to go down and choose from the lower left-hand graph options menu. That's this one that looks like the connected data points within a little mini graph. From there, I'm going to choose apply curve fit. I don't want a linear fit. I'm going to choose just a sine fit here and hit apply. And I can see the pink, this is 2/3 of the way up. The green is the one where it's at the very bottom. And I fit a sine wave. This first fitting parameter A is my amplitude. The fitting parameter D at the very end, this is my, my offset up or down. It should probably be pretty close to 0 because I'm centered around 0. C, remember, this is our phase shift. It moves the wave left or right. In this case, it moves. It's not that important to us. The thing that we want is really this fitting parameter B. This is multiplied by the value on the horizontal axis, which in this case is time. And this is our angular frequency here, a measure of how quickly it's oscillating. And the faster one, where it's at right now, 2/3 of the way up, that angular velocity, this is in radians per second, is 7.726 versus where it was when it was at the bottom, which was 5.45. So it definitely is moving faster. Students will move their way up. You'll see if you look at the lab activity, it has students make a data table, and they start at the bottom and they record like a position and they figure out what the moment of inertia was, and they go through it. They do a number of different calculations, and then they measure and record that value there, that B parameter, the angular velocity or angular frequency. And then they move it up a little ways and they do it again. And then they move it up a little ways and they do it again. And they look at how does that angular frequency change with the length. And how does that compare to, say, like a simple pendulum? This particular activity is definitely geared towards AP Physics C students. The kids that are doing AP Calculus or calculus-based AP Physics. And it actually, in the analysis, asks students to derive the formula for the angular velocity, or for that angular frequency. That is kind of a lot to expect of basically any first-year physics student. I've put the steps in here just because they have them in the lab. I feel like it's a little bit simpler. One thing I do want to show, and if you've seen this before, you've probably seen this, you've been through this process. One thing that they do, one thing that physicists do that they do in this particular activity is they use this small angle approximation. And the idea is that the sine of the angle, as measured in radians, is very close to the angle itself. And I've said that a million times, the small angle approximation. And I was curious, like, really, how much of a difference does it make? And so I went into graphical analysis and I plotted it out. And I plotted out theta versus the sine of theta. My purple data points here are theta, and then the blue data points, you can see it starts to diverge here. That's the sine of theta. And if you look at 15 degrees, usually they say a small angle approximation is good up to about 15 degrees or so. At 15 degrees, they differ by 3 thousandths of a radian, which in the grand scheme of things is about 1.2% difference. So the difference between theta and the sine of theta is only about 1.2% difference at 15 degrees. You can see that as it gets bigger than that, the two diverge, and it's less and less of a good substitution, less and less of a good approximation. So as long as your pendulum is moving relatively small, within 15 degrees, you can make this substitution, you can make this approximation, and get a pretty good estimate. All that to say, this lab, like I said, mentioned before, it comes from our advanced physics mechanics book. It's definitely geared towards, this one in particular is geared towards AP Physics C students in college, calculus-based physics. It's a really cool one. It is when I taught AP Physics, I did not have these rotary motion sensors. And so we did a lot. We would do a simple pendulum, but we never did a physical pendulum like this. And I kind of missed it. There was a lot of math in that particular unit. And I kind of missed having a real hands-on activity like this. So I felt like it would be worth, it was worth showing you today so that you'd have an idea of how you might use that in an AP Physics C class. Let me direct you to the last slide here is just product links. These are the things we talked about today with links to them on our website. That being said, Fran, are there any questions that I missed or things I should explain again?
I'm not sure there are any outstanding questions, but certainly if people have questions, go ahead and type them into everyone.
While you do that, let me just point you towards our website. If you go to www.vernier.com, you'll end up on the, I just chose the page that has the rotary motion sensor on it. But I want to point you to, I'm going to stretch this out so it looks a little bit nicer. I want to point you to, if you go to the professional development menu and then choose personalized request, this allows you to request like personal training, one-on-one training sort of thing. And there is a form here you can fill out. And if you choose under what type of professional development session are you interested in receiving, there's one that's titled Getting Started via Zoom, complimentary up to 1 hour. If you choose that option, you can do a free one-on-one sort of Zoom training with me or Fran or one of our colleagues here. In an hour, we could go through a couple of activities like this together, or we can, we could talk about other stuff. You want to talk about motion detectors or photo gates or whatever, we're happy to do this. I do these sorts of things all the time. They're great. They're super useful. If you have new stuff that you found in the closet that you have never used before, or if you're brand new to Vernier and you want to get some extra help, get started, or you move to a new school and they have a different set of Vernier equipment than your old school does and you want some help with that, this is a great way to do it. These Getting Started via Zoom professional, and it's free. We just get together for an hour over Zoom.
Hey, Josh.
Yeah.
Is this slide deck in the folder?
It is. If you go to the folder, it's this one. It's entitled Angular Momentum in Action. It's that the slide deck there.
All right. So yeah. So you have the slide presentation available to you right now, and it will continue to be available after this webinar. And then a question about the activity. Does the activity have students actually figuring out the location of the bob to get a 1 second time or something so it could be used as a clock?
You could definitely do that. This activity, as written, is very academic. It has them doing, plotting things out and that sort of thing. Definitely like I feel like with most of these activities, the procedure works 100% of the time. It works as written, but they tend to be pretty dry. As when I was in the classroom, the first time I would teach, I would do a lab activity, especially with the Vernier stuff. I would just take it, photocopy it straight out of the book sort of thing. And then after the activity, I'd see how it goes. I'd go back in and I would tweak it. You'll see that what's provided here are PDFs. If you purchase the book, it comes with an electronic version that includes these same files as PDFs, but also in Word document format. And so I would take the Word format and I would edit it. And often I would add in details like that. You might add in, especially if you've got a particular like sequence, you want to kind of tailor it a little bit to how you do your curriculum. I would often tweak the follow-up questions so that it would match kind of like where we were in our sequence. Or I sometimes it would change the language a little bit so it would use the same sort of jargon that like I was using in our classroom. Or I would add things like, now tell me, where does the bob need to be in order to get a period of 1 second, But yeah, those sorts of things are great things to add to a lab like this.
It's also good to think about, all right, so in addition to a grandfather clock, which honestly you don't really see very often, so it's kind of really cool when you do see one, but what other phenomena are out there that you could link to these activities?
Yeah, yeah. Well, thank you all for being part of this. It is we love doing these sorts of things. I hope you found it valuable. I think Dylan, we're still going to do a drawing. Is that right?
That's right. Yes. So, as our presenters were speaking, I went ahead and entered everyone's names into a random name generator, and today's winner is Alan S. So, congratulations, Alan. I'm gonna go ahead and email you. I just need some information to get that gift certificate sent your way. That email is going to go out first thing tomorrow morning, so keep an eye out on your inbox. It'll be coming out from someone with an email domain that ends with @vernier.com. So if you don't see it in your inbox tomorrow morning, that's first thing Pacific time. So I'm not sure where you are, but that will be around 7 a.m. Pacific time. Check your spam. And it will be there. So congratulations.
And just as a reminder to everybody, if you need help, so on our website, there's a chat. We also have a direct phone number, which is 888 something.
Vernier.
It is. Oh, I've got it right here on my card. 888-837-6437. And you can also email physics@vernier.com. And that physics@vernier.com email gets to the entire physics team. Whoever sees it first picks it up. So that's the fastest way to get an email question answered.
Thanks, everyone.
Thanks, everyone. Have a great night, and we'll see you next time.
See ya.
Bye, all.